So now we're going to do problem 5 of the second section of the exam. So problem 5 has 2 parts A, B, and B has 2 parts itself. So now, to find A, so to solve for A, find the limit as the limit of x approaches 0 of tangent of x divided by x. Okay, so how are we going to do this? Let's rewrite this. So what I usually do is just go ahead and plug in 0 first to see if it works. If it doesn't work, that means we need to do more work. So tangent of 0 is 0, and we get 0 over 0, which is undefined. Okay, so that means we need to do more work. Alright, so what does more work mean? Let's try to use some identities and to try to simplify this. Okay, so then we know that the limit as x approaches 0 of tangent of x over x can be also expressed as tangent of x is known to be sine of x over cosine of x, and all that divided by x. Okay? So now, this is the same thing as saying sine of x divided by x times cosine of x. Okay? And that's also the same thing as saying sine of x over x times 1 over cosine of x. Now you may ask, why did I put it this way? Well, I put it down here to recall that the limit as x approaches 0 of sine x divided by x is always 1. Okay? So, the limit of this is equal to the limit of this. So we have x times, now, in the limit rules and the properties for limits, if you have a limit of something times something, you just take the limit of this times the limit of this. Okay, but we already know this is 1 according to this rule, so we have 1 times, now the limit of this is 1 over cosine of 0. Well, we know cosine of 0 is 1, therefore we have 1 times 1, and that's 1. Therefore, the limit as x approaches 0 of tangent of x divided by x is 1. Okay? Alright, now let's do part B. So part B, they give us a piecewise function. They say let f of x be this piecewise function, tangent of x, if x is less than or equal to 0, and it's x if x is greater than 0. Now they want us to compute f of 0. Okay. So to compute f of 0. Alright, to compute f of 0, which of these two are we going to use? Well, we have to use this one because this one only allows for 0 to be on. This one does not allow 0 to be there. So we have to use tangent. So that means we have tangent of 0. But what's tangent of 0? That's 1. Okay? Perfect. Alright, so now, let's see what else. Okay, so use limits to show that f of x is continuous at x equals 0. Alright, in order to show this, we need to show that the limit as x approaches 0 of f of x is equal to just f of x. Okay? Sorry. Tangent of 0 is 0. That's sine over cosine. Sine of 0 is 0. Yeah, sorry. So that's 0. Alright, so where was I? Okay, so yeah, we need to use limits to show that f of x is continuous. So in order to show it's continuous, the limit as x approaches 0 of f of x has to equal f of x. Well, we already know what f of x is at x equals 0, right? Because at x equals 0, right? So at x equals 0. So f of 0 is tan of 0, which is 0. Now, we need to show that this is 0 as well. So, we need to recall that the limit as x approaches c from the left of f of x, if this is equal to the limit as x approaches c to the right of f of x, then the limit as x approaches c of f of x exists. So if these two are equal, then this implies that this exists. Okay? So then we need to go ahead and compute the limit as x approaches 0 from the right of f of x, and we need to see if it's equal to the limit as x approaches 0 from the left. So this is the left, and this was the right of f of x. Okay, so we approach this from the left. We come here, we have to use this one because x values are less than 0, so that means you're approaching from the left. But we know tangent of 0 is 0, so this one right here is going to be 0. Now, is it equal to this one? Okay, let's look. F of 0 as you approach from the right, that's 0. So 0 equals 0. That's true. So since this is true, since they're both equal, then this exists, and if this exists, then it's 0. So 0 equals f of 0, but f of 0 is 0, so yes. This implies that 0 equals 0, and therefore it is continuous. Okay? So let's go ahead and jump to part 2. Okay? Probably going to have to erase some stuff here. So let's read this out. Use the limit definition, f prime of 0 equals limit of x as x approaches 0 of f of x minus f of 0 divided by x minus 0 to determine if f of x is differentiable at x of 0. Alright. So, and if not right, not differentiable. So let me go ahead, well, we'll need that. Okay, let me erase part B. So I'll go ahead and erase part B. And we need to do part C now. Okay, and okay, so to determine if f of x is differentiable at x of 0, we have to compute the limit as x approaches 0 from the left. And if we approach from the left, we're going to have tangent of x minus tangent of 0, which is 0, divided by x minus 0. So that's just x, right? Or x minus 0. Let's put x minus 0. Okay, so, and this has to equal to the limit, so I'm just write down here, limit as x approaches 0 from the right. And if we use it from the right, we have to use this. So we have x minus f evaluated at 0, that's 0, so that's 0 over x minus 0. Okay? So this comes out to be the limit as x approaches 0 from the left of tangent of x over x. But we already know that that is going to be, so this is right here, we already know that's going to be 1. So then this right here has to be equal to 1. Okay? So this is equal to 1. Now if this is equal to 1, we're golden. So what happens here? X minus 0 divided by x minus 0? Well, that's 1. So that's also equal to 1. So since they're both equal to 1, then it is differentiable at x equals 0. Okay? So that's it. Yep. So let's recap. A, find the limit. In order to find this limit, we need to recall that sine of x over x is 1. With that, we can go ahead and use algebra. We get 1. Perfect. For B, we need to compute f of 0, which we did. We computed f of 0. We plug it into here. Tangent of 0 is 0. Good. Use limits to show that f of x is continuous. Okay, in order to do that, we need to take the limit as x approaches 0 of the function, and that has to equal to f of 0. But f of 0 is already, see, f of 0 is already 0, and the limit is also 0, so 0 equals 0, so we're fine. Now, 2, using the definition, we need to determine if it's differentiable at x equals 0. So using this definition, we approach from the left and we approach from the right. They're both equal to 1, so since they're both equal to 1, it is differentiable at x equals 0. Okay, that's it.